Hi. The squeeze theorem is an important tool for demonstrating the existence of a limit in cases where a direct approach is not practical. In this video, we present the squeeze theorem, which is also known as the policeman theorem, in the context of numerical sequences. The intuitive idea behind this important fact is simple. Suppose you find yourself between two officers who are both heading to a police station. Where do you think you will end up? Yeah, I'm sure you already grasped the deepest sense of this theorem. Let's see it precisely. So, assume that we have three sequences, AN, BN, and CN, numerical sequences, real valued sequences. Be such that, first, Bn is trapped between An and Cn, at least for n large. In this interpretation, An and Cn are the two policemen. And second, assume that both An and Cn have the same limit L. It is not important if L is finite or less. Then, also Bn will have a limit, and it will have the same limit of An and Cn. That is, Bn goes to L when n goes to plus infinity. Now, to understand this statement, a good idea is to do some practice on some simple examples. Let's consider this one. We have to compute the limit when n goes to plus infinity of n minus root of n divided n plus root of n. If we look at this number for n large, we may see that it is n plus or minus root of n that are compared in the ratio. Now, root of n is much smaller as order of n, so we may think that both numerator and denominator are more or less like n in size. Therefore, we may expect that this fraction be equal to 1 when n goes to infinity. Now, we could notice that, more precisely, that if we take the number n minus root of n over n plus root of n, clearly the numerator is strictly less than the denominator. Then, since this one is positive, this fraction is less than 1, so we can just write less or equal than 1. On the other side, if we add and subtract root of n in the numerator, we have n plus root of n minus 2 root of n, divided by n plus root of n, and then we split this fraction, obtaining 1 minus 2 root of n over n plus root of n. Now, we may notice that if we take this part here, so let's focus on root of n divided by n plus root of n. We are subtracting 1 minus 2 times this. Now, if I eliminate this root of n from this denominator, the denominator decreases. Therefore, the fraction increases. So this is less or equal than root of n divided n, which is 1 over root of n. So when I subtract this number, I'm subtracting a bigger number, so this fraction will decrease. So it is greater or equal than 1 minus 2 divided root of n. And now look, we have this fraction, which is controlled above by 1 and below by 1 minus 2 over root of n. Now, these two guys are the two officers that go to 1. This one goes to 1, it is constant, and clearly also this one goes to 1. And therefore, this fraction, which is between the two, will go to 1 as well, just because of the squeeze theorem. Now, let's see a second example. Here we have the limit for n going to plus infinity of n factorial divided n to power n. We may see easily that these two quantities are both big when n goes to infinity, but when we take the fraction, in particular n factorial over n to n, we cannot just simplify easily, but we can say that the factorial of n is the product of all integers between 1 and n, so 1 times 2 times 3 and so on, times n divided by n to power n, which is n times itself n times. So n times n times n, and so on until the end. Now, in this way, you can see clearly that the numerator is smaller than the denominator, so the fraction is less than 1. But another remark you could do is that if you split this long fraction into product of n fractions, they are all, of course, less than 1. But in particular, we could do the following thing. We could keep this fraction, save this fraction, and throw away all this because they are just less or equal than 1. This is less than 1, this is less than 1, this is actually equal to 1. But in any case, all this product will be less or equal than 1. So this number, which is less than 1, multiplied by 1 over n, will be less or equal than 1 over n. And since this is the ratio between two natural numbers, it will be also greater or equal than 0. And again, we have the two officers here, 0 and 1 over n, both going to 0. This one because it is constant, this one because we know it is one of the simplest examples of a finite limit. Therefore, also the sequence we have here in the middle must go to 0 for the squeeze, because of the squeeze theorem. An important rule for calculation follows from the squeeze theorem. It is the rule of a bounded sequence multiplied by an infinitesimal sequence. Let an be n two sequences. Assume that an is bounded, and this means that there is a universal constant m, universal with respect to the index n, such that the absolute value of an is controlled by m for every n. And second, Bn be infinitesimal. So this means just that Bn goes to 0. Then their product will be infinitesimal as well, so it goes to 0 when n goes to plus infinity. We can easily understand why this comes from the squeeze theorem, because if you take the product an Bn, since this factor in absolute value is no larger than capital M, and this is, of course, controlled by absolute value of Bn and minus absolute value of Bn below, we have that this is between these two sequences that they both go to 0 because Bn is infinitesimal. So this forces also an Bn to go to 0. And that's why you have the conclusion. You can see a simple application of this rule on this example. We want to compute the limit when n goes to plus infinity of sine n over n. The behavior of sine n can be really very complicated, but we can see this as a product 1 over n times sine of n. Sine of n is bounded because the absolute value of sine is always less or equal than 1, and 1 over n is infinitesimal. It goes to 0, so this limit is just 0. So what are the next steps? First, I would suggest you to practice on the squeeze theorem and the rule bounded the time infinitesimal on these examples, or many others, of not particularly complicated. And then perhaps you could try to challenge yourself on a slightly more difficult problem, like determining these two limits. This one is actually an extension of this, which is a particular case for a equal to. Well, good job.